Password security is one of those things that not a lot of people seem to do much about, but it's actually one of the reasons a lot of people get hacked. A lot of the problem is actually with the strategies that both people and websites employ to secure passwords. We'll look at some of the common strategies here, and at the end of the video I'll show what I think is the best strategy and a program I wrote to help with it. Now, websites always like to make people use a special character or have an 8-digit minimum for the password length and use numbers and capital letters, stuff like that. They also oftentimes like to make people change the password every month. And generally, these things usually hurt security instead of help it for reasons we'll see shortly here. The problems people or customers usually have is they like easy to remember passwords. So people will usually make the easiest password that fits the requirements the website or company makes. People also like writing passwords down to remember them because they change so often that oftentimes causes problems for remembering passwords. Sometimes people also cycle passwords, use old ones. If people were smart, they'd use a password manager, which still has some issues that we'll talk about later, but that's probably the best option conventionally speaking. So to understand the problem here, we need to understand first how websites do, or how they actually should, store your password. This is actually an industry standard, so it's not just something I made up. But the website usually has a server that stores user credentials. This stores your username, and it doesn't actually store your password, but it stores what's called a hash of your password. But basically the user will send their user credentials, their password and username, and their browser will do this hashing function on it. And then it'll send the hash password to the server so the server can verify if that user is who they say they are. So we have to explain here what is a hash in general. And what a hash is basically a mathematical function that'll take in some data and it'll spit out some more complicated looking data that can't actually be predicted based off the input. So it actually destroys information in that the only way to find the result of a hash is to do it actually. You can't take a hash and figure out what was hashed to get that, so it's kind of a one-way function. And it'll always spit out a consistent length of data, so oftentimes it's just 256 bits of random seeming data. So this has ramifications for how hackers actually steal your login info. So normally it starts out by some website getting hacked, and then there's this table produced basically of all the login information, so usernames and hashed passwords, and that either gets circulated on the internet or hacker buys it basically from some other hacker, and they want to use this to steal accounts basically. So they can't just use the hash passwords directly, they actually have to recover the password first so they can log in. And they'll do this by basically writing a program that tries a bunch of different passwords and hashes them. Or sometimes they'll have a list of hacked passwords from a website that didn't hash their passwords, and they'll try a bunch of those. Or they'll try combinations or variations of those. That's actually why reusing passwords or using old passwords is so bad, because sometimes a website that only stored their passwords in plain text gets hacked, and if that has your plain text password, that's actually pretty dangerous, because someone could figure out your real password for other things more easily. So we'll take a look here at the general case for the worst case number of guesses a would-be attacker would have to make when guessing a hash. So we'll let n be the number of guesses in the worst case an attacker would have to make in order to guess a hash. And we'll let L be the length of the password, so the number of characters, and we'll let C be the number of variety of characters, or the number of potential characters that could be in the password. So n would be equal to C to the L. So that means that length matters a lot more than the number of characters you use. The reasoning for that is because if you increase the number of potential characters, that only makes the problem harder according to some polynomial value, whereas if you increase the length of the password, that it increases the difficulty of guessing it exponentially. So in the long term, an exponential is a lot bigger than a polynomial of any sort. So let's look at a quick example of someone using the stereotypical password of 8 characters, capital letter, a number, and a special character, and we'll see how insecure it really is. So if someone does the bare minimum, the best their L value could be is 8, which isn't that good on its face, but it's probably actually worse since they have to use certain special characters or numbers. Since they only have to use one capital letter, one number, and one special character, we could probably assume the rest of their password's going to be just lowercase letters. So using the multiplication rule, that means we have 26 to the 5th power, and it's going to be times 27, because that's the amount of special characters I counted. That might be inaccurate. Times 10, because that's the number of digits there are. Times 26, since that's the number of capital letters there are too. And that makes about 83 trillion possible combinations. Now that sounds like a lot, but it's actually not as much as you think. Now mileage is going to vary a lot here based off computer setup, but back when I was mining cryptocurrency, I remember I was hashing like 63 million hashes a second with my pretty cheap setup. And according to some guy on Reddit, he had a setup that can do 72 billion hashes a second for the Windows password hash. This will also depend a lot on the hashing algorithm, so this won't necessarily always be the case. There might be some very secure hashing algorithm out there, but that won't amount to a total difference in the numbers here. Also, the way I did the multiplication rule here assumes a very specific order, so it's going to actually be a little bit better than this. That's because it assumes you do all lowercase letters first, and then a special character, and then a number, and then a capital. So in practice it's going to actually be a couple orders of magnitude better. That would just amount to someone taking a couple days though, instead of a couple seconds to crack your password. So the main question here is, what can be done about all this? The moral of the story here is that to protect against brute force attacks, really all you need is length, and complexity matters a lot less. So let's say we had a password that only had lowercase letters in it as far as character choices, but it was 15 characters long. We'd have n equals 26 to the 15th power. And if I put this into a calculator, that gives us n equals approximately 1.67 times 10 to the 21. Now, the age of the universe in seconds is approximately 4.36 times 10 to the 17th. That's not quite as secure as it sounds, because I actually did the math, and that Redditor's setup would actually crack this in about 72 years. Now, that being said, you could add one more letter and multiply that by 26, two more letters and multiply it by 26 squared. So there's an XKCD comic where he actually talks about this problem, and he basically determined the same thing that we did, where it's much better to come up with a longer password that's easy to remember than a shorter password that's hard to remember. And he comes up with correct horse battery staple as a very easy to remember password. And in general, I think this approach is good. However, it's probably still good to add a couple bits of entropy there. And what I mean by that is basically choosing words that are less common, and also perhaps mixing in a special character or a capital at the beginning or end. And the reason for that is because if people know you're using this approach, they could actually do a dictionary attack where they just try a bunch of different words. Because then again, it's basically the same as having a password with a ton of potential options, but that's only like 4 characters long. It's just with words instead of characters. So this would be quite secure if the password was made up of words that wouldn't be in any dictionary, and if it included a couple of extra bits of entropy like a capital or a number, or even character substitutions. Another common approach is people use a password manager like Bitwarden, And what that basically does is it makes it so you only have to remember one good password, and Bitwarden stores a bunch of really long, really complicated other passwords for all your other things. And the main problem here is if your Bitwarden gets hacked, the hackers have everything. So I'm actually working on writing my own password manager, and I believe it basically solves all of these problems. The way it solves all these problems is basically it doesn't store the password. So even if your computer gets hacked, then it's pretty unlikely they'd be able to find your password. It allows you to use a bad password, and it'll still generate like a good password for you based off that. And it's easily configurable to make passwords that fit any arbitrary website requirements. So the way my program works is it prompts the user for the website they want to visit, and then it prompts the user for their mastered password. And what it does is it concatenates these two together so that now that's a related piece of data, and then it shoves that through a hashing function. And it might do this multiple times or put it through multiple functions, and then optionally at the end it puts it through a program that makes it look like a real password generated by Bitwarden or something. And it'll do that consistently. And this has a couple of advantages. For one, it'll actually make it so that if the website you're using hashes their passwords, then a dictionary attack won't work at all. In the case that a website doesn't hash your passwords, then at least the master password is still safe with this system, since the final password is still dependent on the website you visit. So this will be a quick demonstration of how it works. Version 2.sh. So basically it's just a bash script, but it uses Zenti, so it actually has like a user interface basically. But there's the basic generation and the advanced generation options. So if we go to basic generation, hit OK, it'll prompt the user for a website. So let's say this is my Amazon password. Amazon. OK. And then my password could be 123, and this is the password it generated. Now currently I believe it only does 10 characters or something, which it definitely should do more, but I just figured that was a common thing for websites. Although the nice thing about this program is it's actually configurable so that you can use more complicated schemes for mixing up your passwords. So if we go to advanced generation, we have create profile and select profile. So if I hit create profile, enter a name for the profile, I don't know, video test, hit OK, and then so it actually allows you to encrypt the profile, so the specific mix-ups you do will be encrypted and saved to the device. So I guess the encryption key I'll just make ASDF so that I can remember it. And then we have these options. So if I go to concatenate, so I can concatenate a string to it. That'll save a string to the profile. So this will append a string, 1, 2, 3, 4, 5, and then that's added to the chain. And then I can SHA-256 that. And what it'll do is essentially successively do all these transformations. I can base 64 encode it. Oh no. I'll SHA-256 it again. Then, oh no, I guess I'll reverse it or something. And then shuffle it like a deck of cards 3 times. And then, I don't know, Caesar Shift 16 it. And then I'll hit finish profile, and it saved it to video test. Alright, so then if we hit select profile, we can go down to our video test. ASDF is the encryption key for it. Website Amazon. I don't know, 123 is my password. And now this is the garbage that it generated for my password. So as you can see, this is very long. No one's ever going to guess this. It's quite secure. I would say. And yeah, that's a quick demo of my program. One thing I should mention before I go is this isn't a new idea. There's lots of stateless password managers. This here is LessPass. This is a website you can go to. The one issue I see with LessPass is it's not open source. So if it goes out of business or something, you might lose your password. But there are open source stateless password managers as well. There's one called Stateless Password Manager on GitHub that I saw. This is Stateless Password Manager on GitHub. And I actually plan on publishing mine to GitHub as well once I clean it up and maybe make it a little better, you know. I might add some transformations. I think also there might be an issue where the way it does deterministic randomness won't consistently do it across machines, and that could be a big problem if someone accidentally lost their password. So I'm going to try to fix that before I post it, but we'll see how long it takes me. Anyway, thanks for watching, and hopefully someone found this helpful.